Welcome to the Fixing the Hyperdrive talk. So let's start with an imaginary full-screen pixel shader. And I just want to show you a high-level view of how it's mapping to the GPU hardware units on NVIDIA GPUs. The SM unit, the streaming multiprocessor, executes the instructions of the pixel shader. And if this pixel shader is doing a texture fetch, the texture fetch request is sent over to another unit, which is called the text unit. It has its own internal texture cache, and if the data is not available in the texture cache, the text unit sends a request to the L2 cache, which sits next to memory partition. So there is one L2 partition per memory partition. So that's a long distance from the SM and text units. If the L2 itself doesn't have the data, it sends a request to the DRAM unit if the texture is in the RAM. That's the physical video memory of the GPU. And at the end of the pixel shader execution, it's outputting a color value to a render target that gets sent to the CRAP unit, which itself sends the data to the L2 cache and the DRAM. We like to measure what we call the speed of light of each of the key GPU units to understand how close the units are relative to their peak performance. And we have a term for that, that's the speed of light, or SOL. And we have a metric name, that's the SOL percentage. That's the percentage of peak performance that a unit is achieving. Or if a unit has multiple subunits, that's the maximum percentage of peak performance across all of its subunits. Then we can gather those SOL percent metrics per unit of the GPU and sort them by decreasing order of the speed of light percentage values. And that gives us this nice summary of the performance limiter of any given workload on the GPU. The highest speed of light unit is the primary performance limiter. In this particular case, I picked up an SSAO pixel shader that is running at 95% of the maximum throughput of the SM unit. And after this primary limiter is coming are the text and L2 units, which are 72% saturated. So that view, single line here, tells me this workload is primarily limited by the SM throughput and then secondarily by the text and L2 throughputs. Now, how do we gather this piece of information using the latest tools? That's what I want to show you by showing you a walkthrough. You can start by capturing a frame from your DirectX 11 or DX12 application. You can do that using Nsight Graphics 1.0, which got released very recently. You just select the executable, click Launch. It launches your app. In this case, that's my SSAO app. Click Ctrl-Z space, and that gives you, that captures the frame and gives you the summary of the frame, the screenshot, the API, and you can type commands if you want to remember what you did. Then you can then build this frame into, it's actually a C++, a set of C++ files that got dumped to disk. You can build it as an executable. So that will be replayed at full speed as an executable. This is done by clicking Build. Once you have built it, you can look at what's inside the Visual Studio solution. It's just raw API calls. So you get all the raw API calls that the application was doing to render the frame. That's useful to sometimes use for experimenting. For example, you can discover that you have redundant calls, maybe in your API stream, and try and comment them out. Or you can even manipulate the API stream. You could even replace certain calls with other kind of calls. You could do maybe replace a shader with another shader. You could do any experiment that you can think of that way, as soon as you're able to replace something by another thing and replay the executable again. That's good for performance experiments. It's also good for debugging, because you can see in this form what exactly were the API calls emitted by your engine. And it's also good for reproducibility, because you can replay exactly the same frame if you want to reproduce your results again on a different GPU, for example, or later you worked on something, and a week after you want to go back to it to verify that you were correct in your analysis, you can still do this. So it's very good to dump frames to disk in this manner. Once you have dumped it and built the executable, you can replay it. There's an easy way to replay here from the Nsight UI, Nsight graphics UI. You then just need to select if you want to reset the state of the resources at the beginning of each frame, because that adds a bit of overhead. So to be conservative, the tool always does that by default. It resets the resources to their initial state, just so that there are no possible image differences between frames. But yeah, you may want to disable it if you're sure that it's not necessary. Then click Connect and Frame Profiler. And then Control-Z, space again. And then you go into the Range Profiler view. That gives you the total GPU frame time for that whole frame. It's measured using vanilla timestamp queries, so it should be the same time as you would measure in your engine, with just one important difference, maybe, that the tool here is locking the GPU core clock frequency. So that means that it's effectively lowering the performance compared to the default clocks. So the clocks are going to be lowered a little bit, but they will be stable. They will always be the same clocks. So when you repeat your experiments, you should always get very similar GPU times and metrics. That's very important. We do that always, and we have the tool do it for you, so you don't need to think about that part. This range profiler is giving you a breakdown of the GPU frame time per perf marker. Here you can see the perf markers in this app. There are just two layers of markers. There is the HBO plus top level marker, and then inside of it there are multiple passes. There is the draw Corseo pass that takes half of the frame, so that's what we want to profile in this case. It has a single render target view, you can see that in blue, and it has a single set of shaders in red. So already you get a sense of what this workload is doing. To profile it, it's very easy. You just click on the box that represents the perf marker, click on it, and it profiles that range of calls. Let's zoom up a bit, and you can see that in the output of the range profiler, you get the top souls that I was talking about just earlier. And that's actually the same application I was profiling. It is SM limited and then text LN2. So that is well, I like to think about these top soul percentages as the performance signature or the main performance limiters of the workload. It tells you a lot about what is limiting the perf and what to do about speeding it up. Our method for speeding up any GPU workload, we call it the peak performance percentage method. It starts from the top soul percentage values, and it starts from the maximum unit, from the unit with the maximum soul percentage. And if that unit has a soul that is higher than 80%, it means that unit is pretty well saturated already. And you should try and remove work from it. So that's one way to optimize, to speed up this kind of workload, is just remove work from the unit that has the highest soul, if that soul is higher than 80%. For example, if that's the SM, you can try opportunistically skipping instructions. Just adding branches, try and skip as many instructions as you can, maybe in some corner cases like skipping sky pixels, if they are skippable and so on. Or you can try even skipping warps by doing early depth testing. So you can try setting up a stencil mask that can skip certain areas of the screen and then rely on early Z rejection to skip launching the pixel shader in those places. That's even more efficient than early exiting in the shader. If you have a lot of math instructions and your SM throughput limited, you can try, and also if the text unit is not saturated, you can try moving math instructions to lookup tables in the text. That will be fetched via the text unit. Or if you know your text throughput limited, and you are doing a lot of structured buffered accesses, and the structured buffered accesses are always accessed in a uniform way, where all the threads are accessing the same data, you can then move the structured buffer loads to constant buffer loads. Because structured buffer loads are performed on the text unit, and constant buffer loads are performed on the SM. So that's another way to move work over to the SM. Now, if the top soul percentage is lower than 60%, that means that this unit is doing poorly, is poorly saturated, and you should try and increase that soul percentage, get it higher somehow. There are multiple cases where the top soul can be low like that. First case is there are idle cycles, that for a fraction of the time in your workload, the unit is doing nothing. It's completely idle. That can happen, for example, you're not feeding the GPU fast enough, or for other reasons, like draining the pipeline. There can also be stall cycles, which are internal inefficiencies inside the unit. For example, if the texture unit is missing in its cache, it has to wait for the L2 to return the data. So during this time, it's stalling on the L2 cache. Or there can also be so-called slow path, which are cases where the soul percentage is low by design for the particular kind of work that you're doing. It can happen, for example, if you're using 32-bit index buffers, because 32-bit index buffers on our architecture are not the fast path, and the fast path is 16-bit. So it's good to know that you should always try and use 16-bit index buffers to hit the fast path. The other well-known case, I think, is using 32-bit per channel, 4-channel textures. Those are textures that we filter at half rate. So you will never reach 100% or close to 100% texture SOL percentage with this kind of format. Now, the assumption that we are making in this range profiling here is that the application has no asynchronous compute. But if it has asynchronous compute, what will happen is that the Nsight capture will flatten all of the async compute workloads into the main direct queue. So that they will still work, but just know that you will effectively look at the async compute workloads separately from the rest. Whereas in reality, it may overlap with graphics work. You will just look at it separately. It can still be useful to understand if you have perf opportunities on the compute workload. If you want to debug, understand the overlap between asynchronous compute and graphics, you can use our new GPU trace tool, which we are going to release soon. You can see it at the NVIDIA booth. Now, I want to show you examples of how to use this general method on different kinds of workloads. The first workload is voxelization on VX11 using UAV atomics in the pixel shader. And we can start with the sanity check. Is this workload CPU limited at all? And there's a very easy way to know that. It's the GPU idle metric provided by this tool. It's the percentage of the GPU cycles that the GPU pipeline, the GPU graphics pipeline, was fully empty. And in this case, it was never empty. It's 0.0%, so it tells you you are not CPU limited at all from the perspective of the GPU. The next thing, as I said, we always want to look at the top souls. The top souls here, in this case, are VPC, SM, and L2. They all are doing poorly. The top one is the VPC unit, which is viewport culling, and right after it is the SM. So we want to understand why all these soul percentages are low. There's something there. And we can look at the SM active percentage. That's the percentage of the time that there is at least one active warp running on an SM. In this case, it's 59.5%, which is really low. It means that for this remaining of the time, the SM has no active warp. And the other interesting metrics here, very interesting, are the number of draw calls and number of wait for idles. By comparing them, we can see that there seems to be one wait for idle per draw call. And then there are actually 3 more. 1 or 2 of them are introduced by the tool itself. And so it seems that every draw call is effectively serialized on the GPU. And in fact, that's what's happening. After digging a bit, we found in this case that this DX11 application, because it's using a UAV, always the same UAV in all the draw calls, the DX11 driver is serializing the draw calls by injecting wait for idles between each of the draw calls. This is done to guarantee that there is a deterministic behavior. And just in case the UAVs would be read and written at the same location by the draw calls, the driver is serializing the draw calls. But in fact, the UAVs are accessed using atomics. The order of the atomics doesn't change the output. So it's totally fine to make these guys overlap. And we can tell the driver it's fine to overlap the calls by just injecting NVAPI calls. NVAPI is our extension API to DirectX 11 and 12. And it's public. You can download it and probably already use it. It's a very easy way to tell the driver hints like this. So you just add a begin UAV overlap and VAPI call at the beginning of the range and end UAV overlap at the end. And the driver knows that it can ignore the wait for idles due to UAV overlap and let these guys execute concurrently. The result is that the wait for idle count goes down from 103 to 3, and the top soul goes from 25 to 52%. The SM active goes to 95.1%, and the GPU elapsed time gets a 1.8x gain. And now, just to recap, in terms of the general method, what we've done here, we started from the top soul unit, saw that it was low, and didn't know really what to do about the VPC being low. So we looked at the next one, which is the SM, also very low, and close to the VPC. It was 21% saturated. And then discovered that the reason why the soul percentage was low was because there were idle cycles in the SM where there were no warps active. By seeing this SM active percentage, we knew the SM was active a lot, inactive a lot, idle. And so, yeah, we digged around and found this. Another example workload is drawing a lot of tiny triangles. In fact, there are 22 million tiny triangles in this case. That's an extreme case of a demo, a tech demo that was drawing a lot of tiny tessellated characters. And in fact, is extremely badly optimized application because all those tiny triangles are contributing to 0 shaded pixels. They are all thrown away. So that's a terrible efficiency there, but it's still interesting because that sort of situation can happen to a lesser extent in a real game. The top souls are PD, and next VPC and DRAM. The PD soul percentage is 64%. The GPU idle is 0%. So this app is not CPU limited at all, but PD is not doing so great. 64%, lower than 80%. And because the DRAM is one of the top 3, it's also interesting to look at the DRAM metrics. And this is the DRAM read utilization. That's the percentage of the memory cycles that there was a DRAM read request active. So it's not too high either, but yeah, it's still interesting to track. What we've done next is replacing, in this particular experiment, is replacing the indices of the draw calls in this workload. Instead of 32-bit indices that the app was doing, we make them 16-bit indices. And for this experiment to be really, to make the experiment easy, I also replaced all of the indices that are greater than the U-short max to 0. So all of the indices that were greater than the maximum 16-bit value, they were replaced by 0. That let me very easily replace them by 16-bit indices. And I got that speed up. The top soul got up to 80%, and the DRAM utilization got down, which makes sense because there are less bytes being transferred across from the video memory to the primitive distributor, which does the index buffer fetch. The GPU time got a 2.1x gain, though. So this shows you that by avoiding the slow path, the index buffer fetches for 32-bit are a slow path, and making them 16-bit, you can get a big gain. And in terms of the method, we just found the top soul was primitive distributor, it was low SOL, and we found that it was using a slow path. Another example workload is a light tile culling compute shader. It has topsols, SM, and then text and L2. But because text is only 3.4% saturated and SM is 41%, it really does, the only limiter is the SM. The other ones can be discarded. There is a very powerful metric for debugging SM-limited workloads. That is the SM issue utilization percentage. That metric, if it's lower than 70%, it tells you that your workload doesn't have enough active warps running active on the SM to hide the latency of the warp. Effectively, the scheduler, the SM scheduler, is not able to find work from other active warps to hide the latency of the warps. It's not saturated. So that's a low metric there. 42.6% means the scheduler of the SM is poorly saturated. And we can look at why this is happening, why it's not able to overlap, to hide the latency of the warps. It's because there are a lot of active warps that are stalling on group shared memory barriers. That's this metric. SM warp stall barrier is huge. It is 43. Anything greater than 20% is high, and this is really huge. So we know that because the SM issue utilization is low and the SM warp stall barrier is high, the SM performance of this workload is completely limited by the group memory barrier with group sig instructions in the shader. Now let's look at what this shader is doing. This is a light culling shader. It has 64 threads per thread group, 2 warps, therefore, and there's this group shared memory barrier. Before iterating over the loops, it has 1 thread per light. It's parallelizing across like that, across the lights. The first warp, if there are less than 32 lights to curl in this frame, will perform 1 iteration of the loop. It will curl 1 light per thread. The second warp, though, because there are no more than 32 lights in this frame, will have no work to do. There is no more work to do. So the second warp will just sync on the group shared memory barrier, do nothing, and wait for the first warp to complete. So the second warp in this example is doing no work except waiting for the first warp. So that explains the super high group shared memory barrier warp stall. And an easy optimization that can be done is just making these thread groups, instead of being 64 thread wide, make them 32 thread wide. And the for loop still works because it has the possibility to iterate multiple times. So you can just keep the same exact code there. And the really cool part about this on our architecture is that because of the SIMT model and the fact that the threads execute their instructions in lockstep across the different threads of the same warp, the group shared memory barriers are free in this case. They are actually automatically skipped by our driver. So the result is that we started from 43% warp stall barrier and got down to 0. There are no more barriers executed at all. Once we make them, the thread group, we make them 1 warp instead of 2 warps. And the topsol, as a result, goes up to 73% of the SM SOL. Issue utilization goes up also. But it's interesting to notice that the SM occupancy, which is the number of active warps per active cycle, actually got down. So it shows you that if you started triaging this situation by just trying to optimize the SM occupancy, you would completely miss the problem. The problem is not the number of active warps at all, and you shouldn't attack this kind of problem by looking at SM occupancy. You should start by looking at SM issue utilization and warp stall reasons. Now, in terms of the method, we found the topsol unit was the SM doing poorly, lower than 60% SOL percentage, and the reason for that were stall cycles. So there were stalls on shared memory barriers. Now, next up is a remarched SSAO shader that I wrote myself. It's not very advanced, just doing brute force remarching in screen space to calculate ambient occlusion. It does 8 traces per pixel, and it traces sometimes you can see the range of the EO effect is quite it's not small, right? It can be quite high. It has a stride of 4 pixels, and it's doing per pixel jittering of the sampling pattern. So it's just a classic way to hide the bending artifacts. You just per pixel jitter your ray directions. And this full screen pixel shader has topsol L2 being 80% saturated. And then next are SM, text. So the reason L2 is so highly saturated is because it's getting so many requests from text. Because text, here we can see the text hit rate is 67%. That's a low hit rate. That's, we'd like it to be 80% or greater. 67% is relatively low. So that explains why L2 is so heavily saturated. And we can still look at the second top SOL unit. That is the SM. Again, look at the issue utilization. It's again low. And the top warp stall reason is this long scoreboard metric. The scoreboarding is the mechanism that the SM uses to track the dependencies between the output register of a texture fetch and other instructions that may consume this register. If there is not enough, if there are not enough instructions between the texture return and the next instruction that consumes the output, the SM will stall. It will have to wait for the texture instruction to complete. So texture fetches can be high latency, especially if they miss in the text cache. They have to go to the L2 cache. This is really long latency, and the SM, if it doesn't have enough warps, is not going to be able to hide that latency. So we see that the scheduler is not able to hide the latency. It's not saturating its throughput. There are not enough active warps to hide it, the latency. And we see that the main reason for that is the long scoreboard active warp percentage. So we know we are text latency limited. So we know all these things. Now we have this clear view. We know we are L2 throughput limited in this case, and also the SM is text latency limited. So that's a clear picture of what is limiting the perf. Without this information, I may think that this shader is fine, but it has really bad pathologies here. So we need to heal it. And the easy solution to fix the L2 high SOL is interleaved rendering. It is rendering the sampling patterns separately. Instead of doing them all at once in one full screen quad, the idea is to exploit the fact that the sampling patterns are repeating in a tiled way, and to process the jitter seeds in separate passes. The jitter patterns are processable. We can process them in separate passes. So all the green pixels here, they can be done in a separate pass, where all of those green pixels will shoot their rays into the same directions. And that will help a lot the texture cache. So the first step for this to work is to take the input depth texture, which is a full resolution depth texture, and transform it into an array of 4 half-resolution textures. So we are taking the data, we're keeping the same data, but just restructuring. And then doing separate passes per sampling pattern. This can be done using separate draw calls, or you could also do it with a compute shader by using a 3D compute shader and using the last dimension, the Z dimension, as the jitter index. And then finally, interleave back all the results in the final pass. Because that's not a bit exact optimization, I have to show you how it looks, the difference. So we started from this. It was 6.77 milliseconds on GTX 1080. And by doing interleaved rendering, it looks like this. So there are a few differences because the samples are not going to be landing exactly at the same locations, but after blurring, it's very hard to know which one is better. In this case, also I picked the jitter on the original case to be 4 pixel, which is perfect for this because I use an array of 16 quarter resolution input textures for the interleaved rendering. So it's a good case for interleaved rendering to work. the really cool thing is that the pre-pass and the final pass, they are cheap. They are really cheap. They are taking only 0.1 millisecond and, each in this 1440p resolution. And the main cost is coming from sampling of the depth buffer for calculating AO. Overall, we get a 27% gain on the entire AO calculation, except for the blur, but yeah. Now, let's look at what happened on the soles. The top sole was L2, and it got down from 80 to 11% of its maximum throughput. And after that was the SM, 56%, and it went up to 78.8%. We can see the hit rate got up, as expected, and that explains why the L2 SOL percentage got down. And the issue utilization got up. And the long scoreboard is still high, though. That's why I highlighted in red here. It's still high. It's 28%. So even though we got big speed up, we may feel happy about the speed up, we are still doing poorly. We know that from issue utilization not being so great, because it's still less than 75%, 80%, so not so great. And we know that from looking at long scoreboard active percentage. The easy optimization we can do is in a ray marching shader like that, instead of fetching one sample per loop iteration, just fetch 2. And that lets the hardware batch these 2 fetches together. So the SM can send 2 texture instructions over to text and then wait for them together. So instead of waiting for one, waiting again for the second one, wait for the 2 together. These 2 are going to be asynchronously processed. And that helps a lot reducing the long scoreboard percentage. You can see this in action goes down from 28% to 12%. But the drawback of doing loop unrolling like that, partial loop unrolling, is that you need to use more registers to process the 2 samples per loop iteration. And the associated calculations, you need to process them all together so they consume more registers. We can see this. The occupancy got down from 39 to 33.8. And the classic reason for occupancy to go down is register increase. It's also possible to check the register count using the tool, but I'm just not going to show this. It's not, I don't have time. But overall, we got an 11% gain just by doing that. Now looking at how it fits into the method, we started from this L2 limited situation and we started from optimizing for the L2. So after doing the interleaved rendering and reducing the texture misses, we got the L2 to be 9.9%. We also looked at the SM having a poor utilization, 56 was, and by removing the long scoreboard, reducing the long scoreboard problem by doing the partial loop unrolling, we got that SM speed of light percentage to be 88.6%. So it is now doing really good. It's still possible to aim for higher SM SOL percentages. As I showed at the beginning of the talk, it's possible to hit 95% of the SM SOL, but it's a bit more difficult if you don't have lower detail information. So anything greater than 80% is really good already. Now I would like to talk about an advanced DX12 topic, which is binding shader resource view descriptors to draw calls. There is something that was not very clearly explained publicly before, and we want to get this right. When you do texture fetches, information that the texture unit needs to fetch. This information is the metadata of the texture. What is the texture we're fetching? What are the dimensions of the texture, the format? And this metadata needs to be fetched from somewhere. The shader is sending over a text fetch instruction with an SRV slot number and a sampler slot number, and the text unit needs to fetch this metadata. It effectively caches it inside of the text unit. That's the TSL1 cache. So it has its own mini cache inside of the text unit for this metadata. But if the data is missing in the cache, it has to fetch it from another cache, which is called the TSL2 cache. That's effectively a level 1.5 cache, which is between the text unit and the L2 cache. And it has a higher capacity, this TSL2 cache, but if it doesn't contain the texture metadata, it has to fetch it from the L2. And that's a long way. It's a long latency fetch. So it's important to minimize the number of cycles that the TSL2 unit is waiting for L2 to return. And the tool tells you if you have this problem. We've exposed this TSL2 stall cycle percentage in the range profiler, and you can see it right below the top stall and GPU idle metrics. If that's high, if that's more than 10% especially, then you should worry about this problem. And I will explain solutions to this. If it's lower than 10%, you may still get a bit of speed up by optimizing it, but it may not be really worth it. All right, let's look at a typical way to bind SRVs to draw calls. If you've done this in your engine, you probably recognize this pattern. So we'll start from, in this case, we have two draw calls. They have the same root signature. We use 3 entries per range. We have a single range, and we need to bind these SRVs to the draw call. We have draw call 1 binding SRV 1 to 3, and draw call 2 binding 1, 7, and 3. So they have actually 2 SRVs in common and 1 SRV different. But the problem is that because these SRVs are living in the same range, we will need to do something inefficient. Let's see what happens. So in DX12, you have to use this shader visible descriptor Heap to set up how the bindings are done. And typically, you also use a non-shader visible heap on the CPU side, just so that you can store all of your SRVs for all possible textures. And then you use a copy descriptor simple to copy SRV descriptors from the first non-shader visible heap to the shader visible heap. These are contiguous in memory, so a single call can copy 3 of them. And then, once you have copied them to your shader visible heap, you can bind them to the root signature of the draw call by doing this call, set graphics root descriptor table. That's very effective and efficient. But now, for the second draw call that we want to run concurrently with the first draw call, we have this SRV that is different. But because it's a single table, single descriptor table, we still have to copy these 3 SRVs contiguously in shader visible memory, in shader visible heap memory here. So these are 3 CPU calls, copy descriptor simple calls. Okay, that's a bit of CPU work, but after we've done this, we can bind them all together again. All right, simple, single call again to bind it, all of the 3 together. And the main issue with doing this, although it is very simple, is that it is causing the texture state caches to thrash. The reason for this is that our texture state caches are using the indices of the SRVs into this heap as tags, but they are not using the SRVs themselves as tags. So in this case, the caches, they don't realize that the SRV1 is repeated twice. So there will be entries that are wasted in the cache. The first solution to this problem is splitting the SRV ranges in the root descriptor. So instead of using one big one that contains the 3, you can split them into 1 entry tables. So you have now 3 tables per root signature. And once you have that set up, you can do the copy descriptor simple again to copy 3 of them at once. But now you need to bind them with 3 calls. Before there was a single call here, but now because there are 3 tables, you have to do 3 calls to bind the 3 tables. And for binding the remaining ones, you again have to do 3 calls again. So this is exploding the number of set graphics root descriptor table calls. And these calls are actually quite heavy. They both have CPU and GPU overhead. The second solution is to just do shader SRV indexing, also known as blindless texture. And this is really easy in comparison, conceptually easy. You track all of your unique SRVs for your frame and put them into your shader visible descriptor heap. There is no longer a need to copy from one heap to another, assuming you have less than 65,000 descriptors for your frame. You can just fill them into your shader visible SRV heap, and then bind them all together. Bind them once. That's a single bind call, set graphics root descriptor table. You bind it, and all the shaders have access to all of the SRVs. But they just need to know which one they need to fetch for each of the texture instructions. And this information, you can put it in a constant buffer. That constant buffer is changing per draw call, because potentially each draw call has different textures bound. But if you put this constant buffer into the root descriptor, the root table CBV slot, it is actually quite fast to change it per draw call. As long as it is a root CBV, it is fast to change it per draw call. So that can work pretty well on the constant buffer side. But there is one drawback of doing shader SRV indexing. It is that each of the texture instructions will have a slightly more overhead, a little bit more overhead injected by the driver, because this is a different type of texture fetch instruction that it requires a little bit more registers and a few more instructions for each of the texture fetch. So it is something to keep in mind. But if you are just doing gbuffer fill, for example, and you are not using the SM much, you know it by looking at top source. You can see, oh yeah, I'm not using the SM, it's more than 60% of its maximum throughput, it may be totally fine. If occupancy is not a problem for you and instruction count is not limiting you, you can just do this. And then you get all the advantages of simplicity, having low number of CPU and GPU binding calls. On the other hand, you can keep doing the traditional way, but then yeah, you have all the CPU overhead of copying the descriptors around and the CPU and GPU overhead of the set graphics through descriptor table calls. But the advantage may be that you can use the same shader bytecode on the X11 and the X12, because there is no need to use the shader indexing. The SRV indexing is a shader model 6 feature, so you cannot use, if you do dynamic shader SRV indexing, you have to use shader model 6. Finally, I want to talk to you about another trick for optimizing the X12 apps on NVIDIA GPUs. That's pixel shader barriers. Pixel shader barriers are lightweight weight for idols. They work only for pixel to pixel shader dependencies, and they are supported from Maxwell and beyond. To use them, those lightweight weight for idols, all you need to do is set up your state before and state after flags of your resource barrier calls to be going from a render target only to a pixel shader resource only. If you do this, our driver will inject a lightweight pixel shader barrier instead of a full weight for idle. And you can measure the number of weight for idols that you have and the number of pixel shader barriers that you have in any given range by looking here. I've done this test on a full screen post-processing chain that was just doing pixel shader passes and got this improvement, 26% gain on this workload. You can see the wait for idle count got lower and the pixel shader count got greater. In conclusion, Nsight Graphics 1.0, it makes it easier for you to export frames to CPP, and it makes it easier for you to build your frames as executable and organize your frames as projects. And so this is really what the direction we're going. It also has these additional metrics in the range profiler compared to previous versions of Nsight, and we are going to keep going and adding more useful metrics publicly. So we encourage you to use the metrics, and I think they are very powerful already. If you want to read more details on the general method that I presented here, I encourage you to go to this blog post. the peak performance analysis method for optimizing any GPU workload. There is also the demo of Nsight at the booth. You have any questions? I would be happy to answer them. Thank you. So I know I've shown a lot of metrics and a lot of stuff. No one has any questions? Well, at least when you go home, you can hopefully try this on your engine and see how good you're doing. No questions? So, oh, yeah.
So a lot of this, and in fact a lot of the Nsight stuff, has been geared more towards pixel shaders and things like that. Do you see more of these tools becoming more compute shader focused in the future?
It is not. I actually don't think it is just pixel shaders. It is because the SM metrics that I showed, issue utilization, absolutely applies to compute shaders. Yeah, there will be more metrics exposed, but do you have specific cases of compute shaders in mind that you can tell me?
Not at the moment. So.
OK, but just know that the SM metrics that I showed, they apply to compute shaders as well, because the SM itself, we're looking at it, it doesn't really matter if you're running a pixel shader, vertex shader, Hall shader, domain shader, compute shader. Sure. Those metrics, they are all working for all shader types.
OK, great, thanks.
Hi, thank you for the talk. A very simple question. For every top SOL, do you also have the associated stalls? Or are there times where you don't know if your utilization is low because of their stalls?
Yeah, it's a good question. I showed for the SM, you have the SM active metric. For some of the units, we don't expose the percentage of idle for that unit. And you said stalls, which is a bit different from idle.
Yeah, I guess it's the difference of the two added, right?
Yeah. But yeah, some of the units we don't expose anything, almost like for example, primitive distributor, the one that fetches the index buffers. You can just see it's high or low, but we don't expose information on it. But the reason for this is that we expose only the stuff that is trusted and we used internally and is verified.
Okay.
We have internal metrics that sometimes we think of them as being reliable, and we try them, and they don't really work reliably, so we don't expose things like that.
Okay.
Yes.
Thanks.
Sure. All right, thanks again.